Okay, great. So next talk is from Alexis Chatzigoulas. Floor is yours.
Hi, can you hear me?
Hi everyone. I would like to thank the organizers for providing me this opportunity to present today. My name is Alexis Chatzigoulas. I come from Kounia Lab, from the Biomedical Research Foundation in Greece. And today I will present you a machine learning tool that we created for predicting protein membrane interface of peripheral membrane proteins, and also the creation of a computational workflow for dragging protein membrane interface of peripheral membrane proteins. This is the outline of this presentation. I will start with the motivation of this project, and then with the creation of this machine learning tool. I will continue with the computational workflow for targeting protein membrane interfaces and the web server implementation that incorporates this workflow. And in the end, we have some conclusions and future perspectives. So we know that 50% of pharmacological targets are membrane proteins. And we also know that abnormal protein membrane attachment is involved in diseases. Targeting the protein membrane interface as a drug design strategy has been neglected so far, possibly due to the complexity of the interface, the limited protein membrane structural information, and the lack of computational workflows for performing such drug design strategy. So this gave us a motivation to create a computational workflow for targeting protein membrane interfaces as a normal drug design strategy. So we know that peripheral membrane proteins have specific membrane binding domains that attach to the membrane. And moreover, in the literature, there are many cases, although not so many, where they found binding sites in these binding domains that are druggable. So our workflow starts with the identification of these membrane binding domains, because usually these are unknown. Then the next step is to apply a protocol for a conformational ensemble generation, because proteins are dynamic in nature and we need to account about that, and find binding sites in these protein membrane interfaces. Then we need to evaluate if these binding sites are implicated in allosteric networks, and if these binding sites are connected with the orthosteric site. And then we can proceed with rational drug design and virtual screening, and then for compound selection and filtering, and in vitro and in vivo assays. In this talk, I will present the first 3 steps of this drug design strategy, starting with the machine learning tool for the prediction of membrane binding domains and interfaces. Currently, in the literature, there are 2 other web servers that predict protein membrane interfaces using the 3D structure of proteins, actually. But these often display false predictions, and also these tools are not implemented in a drug design workflow. They are just limited to predicting the protein membrane interfaces. So our task is to create a novel tool with higher accuracy for the prediction of protein membrane interfaces, and also to incorporate this into a more general workflow for dragging the protein membrane interfaces of peripheral membrane proteins. So the first step is to formulate somehow our problem. And in order to predict protein membrane interfaces, we make the hypothesis that using machine learning, we can predict the protein, the membrane penetrating amino acids, so the amino acids that penetrate inside the membrane. So we did an extensive literature search, and we found 54 peripheral membrane proteins with experimentally known membrane penetrating amino acids. So we retrieved these 3D structures, and we pre-processed them using ACEMD. And then using computational tools such like Protocol, we generated thousands of descriptors acting as features in our task, which are specific features. So then we proceeded with data selection because we prefer better data than main data. So our data set consists of the amino acid of these 54 peripheral membrane proteins, and we split them in training set and validation set. We put 46 out of the 54 proteins in the training set, and we left 8 proteins for the validation set. We removed the amino acids that were in the bulk of the protein because we know that only the amino acids in the interface of the protein can interact with the membrane. So those that are in the bulk of the protein are actually useless in our data set. And moreover, we know that only hydrophobic amino acids can penetrate inside the membrane, so we removed non-hydrophobic amino acids. We also did the same protocol for the validation set. And also we found another 11 peripheral membrane proteins that we left them as a totally independent test set. In the end, we calculated the percentage of identity between all sequences in the training set, validation set, and test set to ensure that the validation and test sets are unbiased and they don't have common information in the training set. So then we proceeded with feature selection because we have a lot of features and most of them are totally useless. So by removing the correlated features and zero-valued features that Protical generated, we had one third maybe of the initial features. And then we calculated the feature importance using gradient boosting machines and extreme classifier, and we removed those that were totally unimportant. From the feature importance, we also validated that hydrophobic amino acids and solvent-exposed hydrophobic amino acids and specific secondary structure elements that are found in the literature are indeed significant for protein membrane attachment. But moreover, we found some new descriptors such as evolutionary conservation and flexibility, because these amino acids usually are in hydrophobic loops, which are highly flexible. So then we proceeded with labeling our data. We made a binary classification problem with amino acids labeled as membrane penetrating and non-membrane penetrating. So the next thing to see was that we have a highly balanced data set with only 167 samples in the membrane penetrating class. So we need to account for that and make balanced data sets, because in balanced data sets, machine algorithms tend to underpredict the minority class. So we created a balanced data set using undersampling and oversampling strategies. The first strategy for undersampling was with CNN, which keeps only the majority class samples that are near the other class samples, making the problem harder. And another data set that does the exact opposite. It makes these two classes more separable. And we also performed oversampling techniques like SMODE, and which generates synthetic samples of the minority class, and also ADASIN, which is similar to SMODE, but tries to infer which points are going to be more difficult to predict, and it generates samples in these regions here. And also a combination of oversampling followed by undersampling to remove outliers generated by SMODE. As a last data set, we keep the initial one, and we used a penalization system, which are class weights, to give to impose something like a bias to the models towards the minority class samples and give higher emphasis on them. So we split our data set in 5 folds, and in each fold separately, we applied these techniques to balance each fold separately to avoid information leak between the folds. And then we proceeded with 5-fold cross-validation in 21 machine learning classifiers. such like SVMs and gradient boosting machines, logistic regression, etc. We don't have enough data to perform deep learning. And then we optimize the hyperparameters for all these classifiers for each one of these 6 datasets, using randomized cross-search validation in the wide range of parameter values for each parameter, and followed by grid search in a small area in the vicinity of the parameters that were found from the randomized search to converge into the best one. And then the output of each one of these classifiers were input to meta-classifiers. We used the voting and the stacking classifiers from them, and we also tried the possible combination of the first-level classifiers. We tried every 2, every 3, and every 4, etc. classifiers, and we used the validation sets to for that to see which combination of first-level classifier is the best, and we found that a combination of a voting classifier of 5 of first-level classifiers was the best combination. Here we can see the results in the validation set. With red, we can see the amino acids that are experimentally known membrane-penetrating amino acids, which were also predicted from our tool, and these are also the true positive. With green, we can see the false negative, and with purple, the false positive. We can see that many false positives are indeed nearby the true positives or in line with the membrane, and these are actually true positives, but these were not experimentally tested in the literature, so I initially labeled them as in the non-penetrating class, but they are actually in the penetrating class. And indeed, approximately 2/3 of the false positives are in fact correct predictions, which increases our score. Then the next thing to do was to compare our results with the 2 other tools that are available in the moment, PPM and MODA. You might know also PPM as OPM, which is a database that holds PPM's prediction. And to compare these results, we included all amino acids in the data set. Before we had only the hydrophobic ones to make the comparison correct with these tools. And by using all amino acids, we found that some false positive predictions appeared, and that's natural because it was not trained with these amino acids. And we discarded these amino acids by making a rule that all non-hydrophobic predictions that are in a distance higher than 14 angstrom for at least one of the predicted hydrophobic amino acids are discarded. So in the end, we found that our tool and PPM and MODA have displayed equal performance, but in some cases, our machine learning model outperforms them, such as in this case of retinoid isomerohydrolase. And here you can see the independent test set prediction. With red, we show the experimentally known membrane interacting regions, and with red amino acid predictions of our tool. And we indeed can see very high precision of our tool. And again, we compared these results with PPM and MODA. And here you can see another test case where our tool outperforms them, the phosphatase B10. MODA also and PPM predicts regions in the opposite side of the actual protein membrane interface and the C2 domain. Then we further manually inspected the false positive predictions, and we observed that many of them are implicated in protein-protein interactions. Thus, we assume that protein membrane interactions and protein-protein interactions are alike, at least in terms of maybe hydrophobic interactions. In the end, we tried our tool in transmembrane proteins having a soluble domain. And although our tool was not trained with transmembrane proteins, we also observed here high precision. Of course, we can see some false positive predictions, but we can see that it is also useful for transmembrane proteins. And also, we made our source code available on GitHub for the users to download it. But then we continue with creating a computational workflow for targeting protein-membrane interfaces. So our computational workflow starts with predicting the protein-membrane interfaces and continues with predicting binding sites in protein conformational ensembles. And this workflow was incorporated into a new web server for ease of access and ease of use. So for the first step, we created the machine learning classifier that I showed you. For the second step, in our web server, one can input, one has three options. So the first one is to input an NMR ensemble. So this is the protein conformation ensemble. The second one is for the user to upload his or her own protein conformation ensemble generated from MD simulations or I don't know, whatever. But we also incorporated Exprose, which is a geometric tool created by Greener that creates a conformational ensemble using geometric constraints in codes, etc. And for searching binding sites in this conformational ensemble, we use P2Run, which is a machine learning-driven method for the prediction of binding sites. And we only keep these binding sites that are in a distance of 5 angstroms from the predicted brain-penetrating amino acid to offer to the user only the binding sites in the protein-membrane interface. And we also offer in the end to the user publication-ready visualization in PyMol, in which we display the predicted membrane-penetrating amino acids with purple and the binding sites that are near these membrane-penetrating amino acids. To make it even easier for the user, we also cluster all binding sites in all conformational ensembles. And we define the best using k-means, and we choose k based on the silhouette score, which is much better than the elbow method. And we provide in the end statistics in the user, such as the number of conformations that each binding site appears. That means how much consensus a binding site is, or maybe the user may want a rare binding site, I don't know. And also some statistics like the mean score, mean capability score, etc. So all of them were incorporated into the web server that we created, which is free and open to all without login requirements. It can be accessed through dream.init.eu. We incorporated a queuing system to avoid job failures due to large workload. And moreover, because each job, depending on the size of the protein, it might take from a few minutes up to hours, and for sure the user doesn't want to wait on the screen for the results. We provide a unique URL for each job, so the user can bookmark it and access it at a later time. So this is also a video example of our web server. The user just have to input the 4-letter BTP code and press upload. There is always the option to upload a structure that the user wants. You can select the chain. I also have subtitles, nice. This video is also available from the website that I showed you, so I'm gonna skip on it. Oh, sorry. So to conclude, our predictions confirm experimental results, and the comparison with other tools shows that our tool outperforms them. at least for some cases. And we also offered the new physicochemical insights for the mechanics of how peripheral membrane proteins attach to the membrane by calculating the fusion importance. Our source code is available in the GitHub, but we also created a web server. So it's easier for the user to use a web server, I think. As a future plans, we plan to devise methods that orient the peripheral membrane proteins in the membrane, because now we only find the peripheral membrane, penetrating amino acids, but we do not orient the protein in the membrane. And this is our next step. And also to design a new method for detecting allosteric networks that might connect these binding sites in the protein-membrane interface with orthosteric sites, in case that these sites are not the orthosteric ones. In the end, I would like to thank Dr. Zoe Kurnia, who provided me with and entrusted me with this project in my PhD. Of course, all the previous and current lab members, and all of you for your attention.
Thank you very much. It was a great talk. Do we have any questions? Yeah.
Thanks for the great talk. I was interested in the slide where you said that the false positives tend to correlate fairly well with protein-protein interactions. I was wondering if you've thought about using this tool, or I guess some modified version of the tool, to predict, like aggregation surfaces for, misfolding proteins or something like that.
I'm sorry, can you repeat the last part?
So I was wondering if you've thought about using this tool in a slightly different application. So for proteins that tend to misfold or aggregate, but the structure of that misfolded aggregate isn't known, isn't experimentally resolved. If you could use this tool to predict the interaction surface for these proteins.
I haven't thought about it. Well, I have to look at it maybe and come back to you. I mean, that's a nice idea. Thanks for this. We can discuss it maybe offline.
Hi, Alexios. Thank you for a great talk. I'm very interested about your methods. And one of the questions is about how you don't increase your data from the AlphaFold structures, doing some kind of alignment with your PB structures and the AlphaFold predicted structures, and see how we're going to deal with this false positive predictions.
Thank you very much for your question. The thing is that, let me go to... maybe here. So our data set consists of peripheral membrane proteins with experimentally known membrane penetrating amino acids. So the problem is not the lack of 3D structure in general, but the lack of experiments in these peripheral membrane proteins to find which are the important amino acids that penetrate inside the membrane. One, of course, can use AlphaFold structures as an input in our tool, but well, you must be cautious because AlphaFolds often misfolds the N or C terminal, and in misfolded regions, our tool is not very good. So those with a small PLD score of AlphaFold, like below 70, we suggest to remove these regions before applying them to our tool.
Yeah, one last question while the next speaker sets up.
For imbalance problem, I just wonder about like oversampling and undersampling actually change the data distribution, that the change of the data distribution can have some like effects on your like model performance, or you think it will be fine?
Well, the thing is that I didn't mention that. In the end, the undersampled data sets didn't perform very well. The best data set was the initial one using weights. And this is due to, I think, the very high imbalance. So when we undersampled the data set, we had something like 300 samples in total, and that's very small number. And when we oversampling 167 samples to the range of 3,000, you generate also a lot of outliers that for sure won't help you. So I think that oversampling and undersampling are useful techniques, but not for such high imbalanced data sets, maybe for 40 to 60 or 30 to 70 ratio in binary.
Thank you.
Thank you very much.
All right, thank you very much. Let's thank
you all.
again.